This lecture will cover Chapter 4 of the textbook and is titled Summarizing Data Graphically. So I want to start this lecture by talking about a famous mathematician and almost really infamous named George Cantor. Now, George Cantor lived through the middle of um, the 1800s up until the early 1900s. And he's uh, considered the father of set theory, a very important field in mathematics. And I always like to talk about George Cantor a little bit because he's actually very controversial and had a rather difficult time as a mathematician. I just want to read you this third paragraph here. The objections to Cantor's work were occasionally fierce. Poincare referred to his ideas as a grave disease infecting the discipline of mathematics. And Kroneker's public opposition and personal attacks included describing Cantor as a scientific charlatan, a renegade, and a corrupter of youth. Kroneker even objected to Cantor's proofs that the algebraic numbers are countable and that the transcendental numbers are uncountable, results now included in a standard mathematics curriculum. Writing decades after Cantor's death, Wittgenstein lamented that mathematics is ridden through and through with pernicious idioms of set theory, which he dismissed as utter nonsense that is laughable and wrong. Cantor's reoccurring bouts of depression from 1884 to the end of his life have been blamed on the hostile attitude of many of his contemporaries, though some have explained these episodes as probable manifestations of a bipolar disorder. So, what could these mathematicians possibly seen as so objectionable? Well, that's sort of a basis for why it's necessary to talk about this idea. Now, what Cantor proposed and later and proved, and what we all now understand as true, is that there are different sizes of infinity. That there's not just one size of infinity. There's actually two. There's a countable and uncountable. Um, um, and of course, he's looking at this from the perspective of the size of a number set and something he called the cardinal number of the set. So let's start talking about this. So what I'm drawing here is a real number line. And I put some integers. I put the integers -3, -2, -1, 0, 1, 2, and 3 on the line. And of course, the arrows indicate that the line goes to the right to positive infinity and to the left to negative infinity. One of the things that's important to understand about number lines is that we often, or generally even, label our number lines with integer values. But the line actually represents many, many more numbers than that. For example, pi is a number on the number line. And root 2 is a number on the number line. And there are many, many others. As a matter of fact, there are an uncountable number of real numbers represented by this number line. And, what does this mean, uncountable? Well, if you think for a moment about the set of natural numbers, okay, and the natural numbers start at 1, okay, these are counting numbers, and then go to 2, and then to 3, and so on. So those and 4 and on down the line there. Those are what we call counting numbers or natural numbers. Now, even though those go on forever, okay, the naturals, I at least know how to count them. For example, I know 1 is the first natural number, and I know to get the next natural number is 2. the same thing cannot be said for the real numbers. For example, if I think about 0, if I start counting real numbers at 0, say, then I have to know what is the next real number after 0. And you can scratch your head with that for quite a long time and hopefully finally conclude that there really isn't a next real number. Now, another thing that I want to point out to you is this idea of being on a continuum, okay? So what I'm doing right now is I'm shading a set of numbers. And if you remember from um, algebra, okay, um, we often talk about intervals of real numbers. So this notation represents all the real numbers between 0 and 1. So how many are there? Well, there are an infinite number. But George Cantor would make arguments like there are more real numbers between 0 and 1 than there are integers on the entire number line. And you might ask yourself, well, how can that be? And of course, many of the very brilliant and famous mathematicians of Cantor's time just said that this idea that there are more real numbers than there are integers is just preposterous. Well, these are the kinds of arguments that Cantor would make. He would argue that you could take the line segment 0, 1, bend it into a semicircle, so now 0, say, is here and 1 is there, and so that semicircle is the exact same length as the line segment 0, 1 here. And then start shooting rays from the center of the semicircle through each one of the integers on the number line. And certainly there's a ray originating from the center of that semicircle that can go through, and I missed one, but that's the idea, that can hit every single one of those integers on the number line and so on. And of course, as I kind of missed -2 there. It's hard to hit them, but I hope you get the idea. Of course, as we approach negative infinity to the left, these rays would just approach the horizontal, and there would be plenty of, there would be no problem in doing this. And so each point on the semicircle corresponds to an integer on the number line. So for example, this point would correspond to 0, this point would correspond to 1. And what Cantor would ask you to notice is that there are all these other intervals in between that also contain an infinite number of real numbers. So one could argue that there are actually infinitely more real numbers between 0 and 1 than there are integers on the entire number line. It's an amazing concept. But that idea has an application right here in statistics. For example, when we look at two different variables, say the number correct or on a multiple choice test, okay, that's going to be a whole number. 0, 1, 2, 3, 4, 5 are the only choices or possibilities we're going to have. So the set representing the possible values for that variable contains 6 elements and only 6 elements. On the other hand, if we think about a beaker, say, that holds 50 or has a 50 milliliter capacity, then what possible volumes are there? If I pour water into that container, the volume of water that is in the container could could be an infinite number of values, and those values are on a continuum. And again, this is why we would draw a number line like this to represent that all those possible values for that variable. So thinking about it back in the chapter 1 kind of idea, if I'm talking about the number correct on a multiple choice exam, then I could display that idea by using the numbers 1, 2, or 0, 1, 2, 3, 4, and 5. And so then I could draw a frequency plot because, and I'll label this X. So, and notice there are no possible values in between. In other words, I can't get 1.5 correct. And so forth. So if we're talking about a particular multiple choice exam, and we're talking about, say, we have 12 students that answered that question, or I'm sorry, I've said that wrong. Suppose we have an exam that has 5 multiple choice of questions or something, and these are the results from 12 students that took them, that some students got zero, or one student got none correct, and the other got 5, or one student got 5 correct, and 2 got 4, and so on. We could ask the question, if we selected a student at random from this class or something like that, we could ask the question, well, what's the probability that X, say, is equal to 5? Or what proportion of these exams resulted in 5 correct answers? And, and we could, again, calculate the probability by simply counting. There are one example out of a total of 12. And so the probability would be 1/12. But again, the type of graph that I would draw would be a frequency plot. And this would be an example of a graph that we could use for a discrete variable. Now, on the other hand, if we're talking about this 50 milliliter beaker or something like that, that we're going to pour some liquid into, right? And say, I don't know, I'll make it up. Say we've got some kind of oh, okay. So suppose this is like a coffee dispenser, or we're testing a machine that dispenses coffee or something like that. And so it has a valve, a timer and a valve, and it pours coffee in, and we do that repeatedly over and over again. And we start to think about, well, what are all the possible values that we could have? Say that is, the range is between 0 and 50. And so then we could ask the question like before, well, so what's the chance? And so again, this is, say, X is the amount of fluid that's been dispensed. We could ask the question, well, what is the probability, say, that the machine dispensed 40 ounces? Mathematically and theoretically, the chance that we actually sample 40 exactly out of this uncountable domain is 0. And you might ask yourself, well, how can that possibly be? Well, the answer is because we have one possibility, one value for X, that's 40, out of an infinite number of possibilities. Now, I can't draw infinity over here. It's tempting to put the infinity symbol in the denominator, but mathematically that's really incorrect, because infinity is not a number. And so we have to really use a calculus concept here. And so what we say is, and I think you've probably seen this before, when you have a fraction where the denominator is allowed to get smaller and smaller and smaller, the fraction, I'm sorry, I said that wrong, where the denominator is actually allowed to get bigger and bigger and bigger, the fraction itself actually gets smaller and smaller and smaller. And so in calculus, what we would say is the ratio 1 over n approaches 0 as n approaches infinity. In any case, that's sort of a complex mathematical idea that you don't have to totally understand. But what you do have to understand is I can't just calculate the probability as simply as I did for the multiple choice exam kind of question. What we end up doing then is talking about drawing a smooth curve. Well, one of the reasons I have to draw a smooth curve now is because every x value in the domain here is a possibility, and so the curve itself represents that idea. And instead of talking about x equal 40 here, we might talk about instead x greater than or equal to 40. And then, rather than talking about the height or something, or the number being the relative frequency, we're going to start talking about areas. So we're going to talk about the area of that corresponds to x values at least as big as 40 relative to the total area. And that area then is going to be the relative frequency. So again, this is the first introduction to this idea, but we're going to use it throughout the rest of the semester. And so it's a really important concept. When we have discrete variables, we can model the distribution using things like frequency plots. But when we have a continuous variable, that's not going to work. And so we have to rely on even more complex mathematical ideas, continuous curves and areas. So let's talk about variables some more in a different way. Let's talk about the types of variables. And in statistics, we have really two types of variables, really three types of variables, but two types and then two subtypes or something. We have qualitative variables, which are things like your religion or zip code or say social security numbers, the kind of car you drive, and there's all different types of examples of qualitative variables like that. And the thing about a qualitative variable is that we really can't do any mathematics with it. For example, if I said, well, I'm going to take a Chevy plus a Dodge and divide it by a Ford, and what do I end up with? Well, that doesn't really make any sense at all. So qualitative variables require a whole type of analysis unique to the nature of being qualitative variables. What we're going the main focus of this course is going to be on quantitative variables. And quantitative variables are variables that involve numbers. And there's two categories of quantitative variables that we're going to study. One is the continuous quantitative variable, and the other is a discrete quantitative variable. One way to keep these things straight is that, generally speaking, discrete variables are something that you count. Continuous variables are something that you measure. So pretty much in statistics, anything that's being measured is going to have to be modeled as a continuous variable. And anything that we can count can be modeled as a discrete variable. So let's look at, let's do it. Hurricane Charles in August 2004 has been blamed for at least 16 deaths. Listed below is information on other major storms and hurricanes that occurred between 1994 and 2003. For each variable, determine whether it is qualitative or quantitative. If the variable is quantitative, state whether it is discrete or continuous. Name of the storm. That is qualitative variable. The date the storm occurred. Date the storm occurred. Now that's a number, right? Well, not always. It could be written as a number, but that's also qualitative. Category of the storm. Again, name only. The estimated amount of damage or cost of the storm. Well, we're counting money here. So first of all, this is quantitative. And and we generally think of counting money, so call that discrete. Number of deaths that occur, that is also quantitative. And discrete. Because again, it's the number of, or a count. Now, we're going to start talking about this idea of a distribution more. The distribution of a variable is just the collection of possible values of that variable, along with how often each possible value occurs. Bar charts are a really useful way to represent qualitative data. So here we have gender by percentage and both by frequency. So again, categorical variable, bar chart's a good way to represent it. So let's talk about some definitions. Data on two qualitative variables are often presented in the form of a two-way frequency table. The marginal distribution of the row variable is found by computing the percentage of each row total based on the grand total. The marginal distribution of the column variable is found by computing the percentage of each column total based on the grand total. The association between two qualitative variables is reported by computing some well-chosen percents in the form of a conditional distribution. The conditional distribution of the row variable given the column variable is found by expressing the entries in the original table as percentages of the column totals, and the conditional distribution of the column variable given the row variable is found by expressing the entries in the original table as percentages of the row totals. If one variable is considered the explanatory variable and the other the response variable, then the conditional distribution of the response variable given the explanatory variable should be examined. All right, well, let's take a look at an example of this. So the New Brew Pub manufactures and distributes three types of beers: a low-calorie light beer, a regular beer, and a dark beer. To investigate the relationship between gender and beer preference, a sample of 450 beer drinkers was selected. After taste testing each of the three beers, the individuals were asked to state their preference, defined as their first choice. The preceding table summarizes the responses. So first we're asked to describe briefly in words of what the value 30 in the table represents. So this is the number of women who prefer dark beer. All right, part B. Using the empty table at the right, use the conditional distribution, give the conditional distribution of beer preference given gender. So the first thing we need to do here is figure out what the row totals are. Since the conditional distribution is based on gender, in order to calculate the correct proportions, I need to figure out what these row totals are. So if I add up all the values across the top row, I get 240. If I add up all the values across this bottom row here, I get 210. So to fill in the table for the conditional distribution, what I need to do is to figure out what percentage, I'll come down here and use a little bit of scratch paper, what percentage is 60 divided by 240? Well, that's 6 divided by 24, and that reduces to 1/4. So that's 25%. I put a 25% in my table here. I noticed that the number of males who prefer dark beer is also 60, so I'll just go ahead and fill that value in. The calculation would be the same. And then, of course, since the row total is always going to add up now to 100%, I can easily fill this table in, or this entry in the table in as 50%. What about this other row? What about these other rows? Well, let's start off by talking about the proportion of women who prefer light beer. That would be 90 divided by 200, or 9 over 21, which is equal to 3/7. 3/7 is approximately 43%. And then again, the number of females who preferred regular beer was also 90, so that would be 40% there as well, leaving 14% for the dark beer drinkers. Now, let's and look at part C of this problem. So based on our calculations on part B, should the new brew pub initiate a single advertising campaign for all of its beers, or should it tailor its promotion towards different target markets, such as male versus female? Well, I would say that it might make sense to do some kind of targeted advertising. Again, I think you could interpret this in a number of different ways, right? Um, I mean, if half the guys out there prefer regular beer and new brew pub has a regular beer they want to promote, it might make sense to target that um, regular style beer to the men, and it may make sense to look at maybe one of their lighter beers or something for women, or maybe they do want to do a single campaign just targeting the regular beer. All right, so the last part of this question here, we're going to talk about looking at ways to draw this in some sort of a graph. So let me think about, or let me show you how we could represent this information as a bar chart. So first thing I'm going to do is I'm going to set this thing up, these axes up. So we could look at this horizontal axis, say, as representing the different types of beer that we're considering. And let's see. I'm going to label this relative frequency, and these are going to be in percents. So now what I could do is come through and draw a histogram, or not histogram, I could draw bars. So what I'm doing is I'm drawing a bar for the proportion of males who like light beer, and then do the same thing here for females. And let's see, so 50% of males like regular beer, and only 43% of the females like regular beer. And let's see, got 14% females, and then 25% again for males. So, and then the other thing, so now I got one of the things I might want to do is maybe some color coding here. So maybe I want to shade all of the male bars with blue. Now, I should also mention that, there are always going to be multiple ways of drawing these graphs. There's really rarely ever going to be one way, and that's the correct way. And, you can get really creative with, how you do this. The idea is to display that information in a way that's clear and easy to understand. And we might have some legend um, that describes, say, what the different color combinations here mean. All right, well, that does it for this lecture. I'm going to be making another lecture for part 2 and talk about some different types of graphs as well from chapter 4. So I'll see you next time.